Welcome to This Explainer. Today, we are diving headfirst into the invisible, totally unbending laws of physics that govern everything from extreme theme park thrills to our sheer everyday survival. You know, when you look at a speeding car, a roller coaster, or even a swinging pendulum, you probably just see moving objects. But if we look at them through the lens of a physicist, we actually see this incredible, delicate balance of fantastically powerful invisible forces. And today, we're going to see what happens when those forces are pushed to their absolute limits.
So let me ask you a seriously wild question. Would you bet your own life on a mathematical equation being absolutely correct? I mean, it's one thing to solve a physics problem on a whiteboard in a classroom, but it is an entirely different experience to actually stand in the path of a lethal object, trusting that the conservation of mechanical energy is going to keep you completely safe.
Here's our quick roadmap to answer that question today. First, the pendulum of life and conservation of energy. Second, the roller coaster magic of height. Third, impulse and salvation in a collision. And finally, bouncing versus sticking.
All right, let's jump straight into part 1, the pendulum of life and the conservation of energy. Picture this, a massive 15-kilogram solid steel ball hanging at the end of a long rope. If you lift that heavy wrecking ball just 1 single meter off the ground, you're loading it up with about 150 joules of gravitational potential energy. Now, to put that into perspective for a second, 150 joules of kinetic energy hitting you in a concentrated spot, that is more than enough to be completely lethal. If you were to step into the path of that swinging steel bob, the impact would be devastating.
But what if you wanted to test that math? Well, in a legendary MIT lecture, Professor Walter Lewin literally puts his life on the line to do exactly that. He pulls this 15-kilogram steel bob right up to his face, practically touching his chin. He stands completely, utterly still and releases the ball without giving it even the tiniest push. He just lets it drop. It swings all the way across the room and then comes rushing right back at his face at top speed. He doesn't flinch, and miraculously, it stops a mere fraction of a millimeter from his chin.
So how did he not get his face smashed in? Well, it's all about mechanical energy. Energy cannot be created and it cannot be destroyed. The pendulum converts its initial potential energy into kinetic energy as it drops, hitting its max speed at the very bottom. As it swings back up toward his face, all that kinetic energy transforms perfectly back into potential energy. It literally cannot go higher than the exact spot it was dropped from. And actually, thanks to a tiny bit of energy lost to air drag acting as an invisible safety cushion, it stops just barely short of where it started.
Okay, moving on to section 2, the roller coaster and the magic of height. That exact same rule of energy conservation that saved the professor? It's what keeps you from falling out of massive amusement park rides. Imagine sliding a roller coaster car from a resting point into a perfectly frictionless track with a loop. What's the absolute minimum starting height you need to clear the top of that loop without gravity pulling you straight down? Intuitively, you might think, oh, just start a tiny bit higher than the loop itself, right?
Actually, wrong. It turns out the crucial rule here is a totally counterintuitive constant. You must start from a height of at least 2.5 times the radius of the loop. So if the loop has a radius of 10 meters, meaning it's 20 meters tall overall, you can't just drop in from 21 meters up. No way. You literally have to start from at least 25 meters up. If you start from anywhere lower than 2.5 times the radius, the car simply won't make the circle.
And here's the brilliant reason why. Survival isn't just about having enough energy to reach the peak, it's about having enough speed when you actually get there. Gravity demands a specific centripetal acceleration at the very top of the loop to keep the car pressed firmly against the track. The math's right there. Velocity squared divided by the radius must be greater than or equal to gravitational acceleration. The only way to guarantee you have that exact leftover kinetic energy at the top is to drop from that magical 2.5 r height.
Let's pivot to our third scenario, impulse, and how physics brings salvation in a collision.
Stepping away from the theme park for a second, let's think about our daily commute. We all know that an unbalanced force changes your momentum, but the amount of time that force actually takes to stop you, that is literally the difference between life and death. If you're in a crash and hit a rigid windshield, your body comes to a violent halt in about 0.002 seconds. But if you hit a deploying airbag, that time stretches out to half a second.
This all comes down to the impulse momentum change theorem. Impulse is equal to force multiplied by time. And here's the kicker. Your change in momentum during a crash is a fixed number, right? You're going from highway speed down to 0, no matter what. Because that momentum change is locked in, force and time are inversely proportional.
Let's look at the real-world numbers here because they are absolutely staggering.
Imagine a 50-kilogram person stopping from 35 meters per second. Hitting an airbag extends the stopping time to half a second, resulting in about 3,500 newtons of force, which you can survive. But the windshield, it stops you in 0.002 seconds. That is a 250-fold decrease in the time of the collision, which causes a lethal 250-fold increase in destructive force. That's exactly how airbags use physics to save lives. They literally just stretch out the clock.
And that brings us perfectly to Section 4, collision physics, specifically the difference between bouncing and sticking. So, whenever objects collide, momentum is always conserved, always. But kinetic energy? That is a completely different story. In an elastic collision, the objects bounce apart and kinetic energy is beautifully preserved. But when cars crumple up in a horrible accident, they are experiencing an inelastic collision. The metal deforms, it heats up, it absorbs mechanical energy, and the objects ultimately stick together instead of violently bouncing backward. Think of two billiard balls cracking into each other. That's an elastic collision. The total momentum before the crash perfectly equals the total momentum after. The collision just cleanly redistributes the momentum between the balls, passing the speed from one to another as they bounce away in opposite directions. It's like a perfectly balanced equation in motion.
But in an inelastic crash, things get messy. Because the objects physically stick together, like two train cars coupling, or two automobiles mangling into one piece of wreckage, the two masses combine into a single, much heavier system. And since the total mass just shot up, this newly fused wreckage must move away much, much slower just to perfectly conserve that initial momentum from before the crash.
So, think about it. Everything from airbags cleverly stretching out your impact time, to roller coasters leveraging that magical 2.5R drop height, to a heavy steel pendulum stopping a millimeter from a professor's face, it all proves that physics is constantly working behind the scenes to keep you alive. But if classical mechanics dictates our physical survival with that kind of precision, what other invisible laws of the universe are pulling the strings right now without you even realizing it? Thanks for joining me on this explainer, and stay curious.